Okay, hi everyone. Second lesson on magnetic fields. What we're looking at for this lesson are the forces that are on charged objects in magnetic fields. So, just going to cut to the first slide. Now, if a charged object is moving in a magnetic field, the magnetic field exerts a force on the charged object. So, for something, what we're going to look at is for something to have a force on it due to a magnetic field, it needs to have a charge, the object, and it needs to be moving within the magnetic field. Those two requirements, otherwise there's no magnetic force. Swivel has suddenly gone stupid. Please stop being stupid, Swivel. Now we represent this using an equation, which is F equals QVB. We've got three things to that. The charge of the object that we're dealing with, the velocity of the object that's moving with, and the strength of the magnetic field at the location that the object is at. And it makes sense that, like I was just saying, if there's no charge, there's no force. If there's no velocity, there's no force. If there's no magnetic field strength, then obviously there's no force as well. So force is the magnetic force in newtons. Q is the charge, remembering that it's in coulombs. V is the velocity of the moving object in the direction perpendicular to the magnetic field. That's a very wordy definition, and it's going to come back to matter that it is so wordy when I do a second example. B is the magnetic field strength. It's got units of the Tesla, which gets a big capital T. Now, I said last lesson that we're not going to look at how you calculate magnetic field strength of a particular setup. You might get a question where you're like, well, there is a force of 10 newtons on a charge of 5 coulombs moving at the speed of 2 meters per second. What is its magnetic field strength? You'll get questions like that. You just won't get a question like, here's a bar magnet, it's this long, what's its magnetic field strength? Something like that. This force just gets called the Lorentz force. It's got a T in it. We looked at something called the Lorentz factor when we did relativity. That didn't have a T in it. I don't know, I just forget whether or not you put the T in it sometimes. But yeah, two different things with sort of similar names. Just don't mix them up. So yeah, B is the magnetic field strength, how strong the magnetic field happens to be at a particular point. And just like, well, we're just going to assume the magnetic field strength tends to be uniform from point to point. Now, this is the sort of setup that you see when you're dealing with magnetic fields. Before, when we did magnetic fields between, say, North and the South Pole, or just between the ends of a bar magnet, it was kind of curved. Often when we're dealing with magnetic field lines, we're just going to assume that they are straight in a certain region. So here, red lines indicate the direction of the magnetic field. It's going to point up at all points, kind of like just the solenoid that I did at the end of the last lesson sort of tilted. So we're assuming a constant magnetic field strength between point to point in a constant direction as well as part of a question like this. Now the question is, find the magnitude of the force on the electron below. Now you've got your electron, you've got a magnetic field strength of 0.1 Tesla. It's moving at a velocity of 6 times 10 to the 7 meters per second. So this is a pretty simple question. You've got the magnetic field strength, you've got the velocity, again, the charge of an electron, 1.6 times 10 to the negative 19 coulomb. I left that off because it's an electron and its charge is just a standard number that you would get, I believe, on a formula sheet as part of your exam. It's good to remember anyway. So the force is just those three quantities multiplied together. 1.6 times 10 to the negative 19 times 6 times 10 to the 7 times 0.1 gets you 9.6 times 10 to the negative 13 newtons. So it's just a simple, here are your quantities, put them into your equation. If you know the equation and you don't stuff up on the calculation, it's a very easy question. The next one's going to kind of indicate why I was talking about that wordy definition for velocity a moment ago. So it's the exact same thing. Find the magnitude of the force on the electron below. Again, I've said this before, I just use a number of 1.6 times 10 to the negative 19 when I'm doing magnitude questions. A magnitude is always positive, so I kind of disregard that the electron has a negative charge and just use 1.6 rather than negative 1.6 times 10 to the negative 19 as the charge. Just in case you're wondering why there's no negative on there when I'm talking about an electron. So now the electron's velocity is not perpendicular to the magnetic field. So if I jump back, you can see that here the magnetic field lines were pointing up, the electron was moving to the right. There's a 90-degree angle in between those two things. So the electron's velocity and the magnetic field, those were perpendicular to each other, and I could just use this equation. I didn't have to care about the direction that the electron was moving in. But now I've got an angle between the magnetic field lines and the electron's velocity that isn't 90 degrees. Now it's 60 degrees. So I'm going to have to modify my equation to take account of that angle. And the way I do that is I introduce a sine term, sine of the angle, where the angle is between the magnetic field lines and the velocity of the electron. So here I've got a 60-degree angle. Just as a side note, if I was to use this equation for the question that came before, here I had an angle of 90 degrees. If I had sine of theta on the end and I put in sine of 90, that just gets me a value of 1. So I'm multiplying all this by a value of 1 and nothing is changed as a result. So if I chose to approach a question like this, the same way I'm approaching the next question by actually thinking about what the angle is, then it's not going to affect anything. I can do it in that more difficult way. The more difficult way just simplifies down to this when you've got the electron's velocity and the magnetic field lines perpendicular to each other. So this is the more easy one where they're perpendicular. This one's, it's not really that much harder, but it does have an extra bit to it where you have to account for the angle because they're not perpendicular. So my numbers are exactly the same, magnetic field strength and velocity. Well, I guess the speed's exactly the same. The velocity is different now that it's pointing in a different direction, but the magnitude of the velocity is the same. So because I've got that sine of the angle in between them, I have a sine 60 on the end, and as a result, I'm going to get 8.5 times 10 to the negative 13 newtons. Now, that's going to be less than what I had before, which was 9.6 times 10 to the negative 13. The force of the magnetic field on the electron has decreased because the angle between them has become less. In the case that you had the electron moving in the direction of the magnetic field lines, so they had an angle of 0 degrees between them, they were parallel, there would be zero magnetic force on the electron due to the magnetic field lines. So just keep that in mind. Maximum force when they are perpendicular, minimum force when, well, not minimum force, but zero force when they are parallel. This is a concept that's going to matter in our next lesson when we start looking at motors and how they work. So just keep in mind the direction between the velocity and the magnetic field lines plays a part in determining what the force is. Either it might be a maximum or zero or somewhere in between. That's just going to depend on the angle. Now, that question was about finding the magnitude of the magnetic force on the charge. A force is a vector quantity, it has a magnitude, it also has a direction. So this next part is about determining the direction of that magnetic field on that charge due to the magnetic field. So to determine the direction of the force on a charged object moving in a magnetic field, we use the right hand slap rule. So called because it looks like so the convention we use is that your fingers point in the direction of the magnetic field, your thumb points in the direction of the, what have I done? Current. It says current, but it's basically in the direction of the velocity for a positive charge. So if you remember from last lesson, we say that current is the direction of positive charge movement, even though that's not actually true. But we point our fingers in the direction of the magnetic field lines. We point our thumb in the direction of the velocity of a positive charge. We'll be using this exact diagram when I do an example a bit down the line. And then if you have a line going straight out of the palm of your hand, so the arrow that's shown there, that's going to be the direction of the force on a positive charge. So if I knew that my magnetic field was pointing that way and my thumb was pointing that way, which was the direction that a proton might be moving in, then the direction of the magnetic force on that proton would be out this way, out from my hand, out of the board, out of the page is what we tend to say, because when you're writing on an exam, you're writing on paper, you're writing on a page, so the direction is going to be out of the page. That's just the notation that gets used. If we had an electron rather than a proton, a negative charge rather than a positive charge, the magnetic field lines would still be moving in the same direction. If the electron was moving in the same direction as the proton was moving, then my thumb would be in the same direction. But now that I've got a negative charge rather than a positive charge, the direction of my force is going to be reversed. So if I set up my right hand slap rule for an electron moving in that direction with the magnetic field lines in that direction, the arrow is going to point out of the palm of my hand. For an electron, I've actually got to reverse that and say it's going to be moving in the force will be in the opposite direction to what it would be on the positive charge. So with your right hand slap rule, just keep in mind that it applies to a positive charge. If you're dealing with a negative charge, then once you know the direction, what it would be on the positive charge, you have to reverse that to get your answer for an electron for a negative charge. So when we're talking about this, obviously the convention that we introduced last lesson where we said out of the page is going to be a dot and into the page is going to be a cross, that's going to be convenient because if I had to draw the direction of the force on the proton, I would draw a series of dots showing that the force is coming out of the page. If I had to draw it for an electron, I would show a series of crosses that the force is going to be pointing into the page. So that's a convention that we're going to carry over into this lesson. Now, the example here is what is the direction of the force on the electron shown below. Exact same picture from before, as you can see. I'm going to point my thumb to the right because that's the direction of the electron's velocity. I'm going to point my fingers upwards. That's the direction of the magnetic field. And I can see that my arrow is going to be pointing out from the palm of my hand. That would be the direction for a positive charge. An electron is negative, so I've got to reverse my answer and say that the force on it is going to be into the page. So you've got to keep in mind a few things when we do these calculations: where the velocity is going, where the magnetic field strength, magnetic field lines are pointing, and whether the charge you're looking at is positive or it's negative. That's going to determine whether you need to flip your answer at the end. It's called the right hand slap rule. I said this last time. If you use your left hand, then you'll get the opposite answer that you expected to get. There's a cheat way where... So if you imagine doing the right hand slap rule for a positive charge, I said that at the end you have to reverse it for the negative charge. If you do it with your left hand, you'll get the reversed answer. So if I went back and did this with my thumb to the, thumb to the right and fingers pointing up, I get straight away to my answer that the force on an electron is into the page. You might figure out, even if I hadn't told you that you can do that, that if you're supposed to flip your answer with this hand, then why don't you just use this hand and not flip your answer? Maybe this sounds confusing, and the point is that people do get confused about this. I recommend just stick to your right hand slap rule. You get your force for your positive charge, you need to reverse it for your negative charge. Don't try using one hand for one charge and one hand for a different charge. People try and do that and they often make mistakes because of that. It seems clever, but it tends to lead people to make mistakes and get things wrong. So I know I'm kind of recommending something, well, I'm telling you about something and telling you not to do it, but, don't do it. So if a wire is carrying a current, the current can be thought of as a flow of positive charges, like I've been mentioning, even though in reality current is due to the flow in the opposite direction of negative charges. There is a force on a current carrying wire. We calculate the magnitude of that force using this equation, F equals NBIL. This is an equation where you've got an I for current and an L for how long the wire happens to be, and I and L are very similar letters when you don't draw things on top of your eye or you don't draw L as being particularly curved. So just keep that in mind if you're looking at this equation. You've got an I and you've got an L, and since they're right next to each other being multiplied together, it doesn't really matter which one's which. This could be the L, that could be the I, who would care? But just keep in mind two symbols that look similar but mean different things. It's valuable not to mix them up. Anyway, F is the force of the magnetic field on the current carrying wire. Current carrying wires produce magnetic fields. They're affected by magnetic fields in turn. So if we have a wire carrying a current within a magnetic field, stop doing this swivel, I swear to God. Now I'm covering it up. Let's see if I can get this back to the way it should be. Yeah, that works. So if we've got a current carrying wire in a magnetic field, there is a force on that current carrying wire. That's what this force would happen to be. We calculate it through a few things. The obvious ones are, I didn't even put up what B is. B is the magnetic field strength, same as it was before. I is going to be the current in amps, L is going to be the length of wire within the magnetic field. You'll see what I mean by within the magnetic field when I switch over to the next example. N is the number of turns or loops of wire. So if I should have brought more wires. If I have one loop of wire, then this is a single loop. If I had the second wire and I was to wrap them around, I'd have two loops of wire. And that's going to, well, my factor for N would go from 1 to being 2. My force on it would double because I've got twice as many wires wrapped around, twice as many turns or loops in the wire. When you're approaching questions, you'll often get told something like, you've got a wire, it's a meter long, there's 10 amps of current running through it, the magnetic field strength is whatever value, and they don't make any mention of how many loops of wire there would be. If they don't mention it, you can generally assume that it is one loop of wire and that your value of N would be 1. If it's going to be like 20 loops of wire, then they explicitly state that. With that in mind though, this is something where careful reading and remembering information that you've been given can be useful, because often a question at the very beginning will say a loop of wire has 20 turns, and then there's a part A, there's a part B, and then for part C, you're required to calculate the force. Well, in part C, it doesn't tell you how many loops of wire it has. That information was given to you right at the start of the question, back in like the stem of the question. And you're assuming that since part C doesn't tell you how many loops it has, that it must be 1, even though at the very beginning it told you it was 20. So just keep that in mind, that information about the number of loops for a lot of questions gets put at the very beginning, and then you're expected to use that information later on. It's not given to you later on. So it's just a thing where if you get a question about this and you need to know how many loops of wire there are, go back from the start and look over the question and see if that information is given to you. If it's not, then you can assume it's going to be 1, but it might be hidden there. It might not jump out to you in the spot where you'd expect it to be. So just keep that in mind when you use this calculation. A lot of questions are structured like that. Now, do I want to use my prop for the next bit? I don't know, it's nice having something in my hands. Example, a wire carrying a current of 2 amps with 5 turns of wire is located in a region of magnetic field 30 centimeters long with a uniform magnetic field strength of 0.02 Tesla. Determine the magnitude of the force on the current carrying wire. So, what was I talking about? So we've got our setup here, North Pole, South Pole, field lines pointing straight across from north to south. This is often how we draw field lines, no curviness to the field lines, just straight from north to south. You'll see it set up like this when we do stuff on motors in the next lesson. We've got our wire, which is carrying current. That wire happens to be carrying 2 amps of current, and the width of the magnetic field between here and there, we're going to assume the magnetic field is confined to that region, even though there'd be a bit coming out. That's going to be 30 centimeters long. So if I was told that my wire was a meter long, for example, and given this other information exactly as it is here, and I was asked to do a calculation, the L in my equation is what length of the wire is located within the magnetic field. So it doesn't matter how long the wire is. All that matters is the part of the wire that's located within the magnetic field. So if my wire was a meter long, I'd still use 30 centimeters as my length, because that's the length of the wire that's located within the magnetic field. So just keep that in mind, that's something to keep in mind. Not how long the wire is, but how much of it is in the magnetic field. Often the whole wire is in the magnetic field, but sometimes it won't be. Now this is just a simple plug it in type question. My force on the wire is going to be 5 loops of wire. Magnetic field strength is 0.02 Tesla. 2 amps of current and 0.3. Converting my 30 centimeters into standard units of meters, that gets me out 0.06 newtons. Now, just like how there was, this isn't written up there, but hey, it's conveniently on there. Just like how there was a direction of a force on a charge moving in the magnetic field, because a current carrying wire can be thought of as a series of positive charges moving in a magnetic field, there's going to be a force along this wire as well. And we can determine the force on that wire, like I had on that diagram about the right-hand slap rule a while ago, by saying that we position our fingers along the direction of the magnetic field. We have our thumb oriented in the direction of the current. So current running from there to there, that's the direction of our thumb. And there is a bit of an angularity to it that makes it a bit hard to set things up, but you can see that the force is going to be pointing down as a result. So because the current is thought of as being positive charges, our thumb goes in the direction of the current, our force is going to be pointing right down. Now, the other thing to keep in mind is that this equation, F equals NBIL sine, F equals NBIL, this applies when the direction between the current and the magnetic field lines happens to be 90 degrees, when they're perpendicular to each other. If there was some kind of angle between the current and the magnetic field, then we'd have to modify our equation by adding a sine theta onto the end of the equation, the same way that we did when we were looking at the force on a charge that was moving in the magnetic field. You all right there? All right. So just keep that in mind for this equation. It's the same as when we did the F equals QVB at the, I think it was the very beginning, losing track of stuff. When we had that equation, we had to modify it when they weren't perpendicular to each other by adding a sine theta onto the end, where theta was the angle between the direction of the, well, its current in this case, and magnetic field lines. And just like before, if there is an angle of 0 degrees between the current carrying wire and the magnetic field lines, if they're parallel to each other, there's not going to be any force on the current carrying wire. So there needs to be some angle between them, otherwise it's zero force. The force on the wire is going to vary depending on the angle between a maximum of NBIL when they're perpendicular and 0 when they are parallel to each other. So just worth keeping in mind, this works the same as the example that we were looking at earlier in the lesson. That's the stuff on current carrying wires. Should be starting on, I think it's 2.4, which is what this, I'll fix it up if I'm wrong, stuff is about, and getting some of those ed roller questions done.